so I can't see anybody, but all right. Okay, go ahead, you're up.
All right, we are a Shamble Squad engineering firm, and we made the piano lift. Here's just our design brief. The problem statement was that people couldn't move heavy objects such as pianos, and that crowd is mainly primarily rich people, moving a piano from ground level to a higher elevation. Thus, the piano lift was born.
And it can be used for other things, like lifting cars, just getting a better mechanical advantage on a crane. It can be used for anything, just pianos in this particular situation. A little bit of brainstorming that went into it. We went from a few different things. An initial pulley over on this side, just to work it. We thought about using a screw, just a fixed pulley. I mean, we went through a bunch of different steps to try and figure out which worked the best. In hindsight, a screw probably would boost it a lot, but it would be worse. It'd be even slower, and the efficiency would be even lower. So we finally decided on doing this one right here, which is the initial pulley. That way we can figure out how much our actual mechanical advantage is with our initial force. And then we can just turn the initial wheel here to start the gear chain, works a wheel and axle, and then we have a IMA of 7 on our block and tackle right there. So, and then that's just, we had to to test it, we had to wind a string around our initial, just enough so we can figure out how much force it takes to work it. Okay. So next is our decision matrix.
And on this, we chose the pulleys, wedges, screws, gears, levers, and wheel and axle as our choices. We left the incline plane out because we really didn't like that. Over our choices, we chose the pulleys, gears, and wheel and axle because I guess we like those most. And screws, they couldn't really help us in our machine. Final sketch.
So this is just a view of our gears without anything else. So we have the initial small, then it moves up to a bigger, and they're all connected. And then they're connected, the small and the big gears are just connected by an axle to just multiply our gear ratio increasing. And this is a side view to show this is our pulley system here, connected to the wheel and axle, and then our gear chain, all connected. And then it's our final, just wheel and axle to initiate the movement. And here's a semi-isometric view to show our 10 Newton weight, our height of 24 inches, and our block and tackle, our wheel and axle to bring up the weight, and then our depth and our length. Okay, and this is our media display. So a video of it working like you saw just before. So we pull the string slowly so the gears don't come apart, and then our weight eventually moves up because our wheel and axle back here is moving our first small gear on our gear chain, increasing our torque 3 times over to get a gear ratio at 12.17 because it's 84 tooth gears and 36 tooth gears, and it'll slowly but surely move on to the extra wheel and axle back here. And when that moves, it pulls the string for our block and tackle with a mechanical advantage of 7. And then slowly but really efficiently, because it takes basically no effort whatsoever to pull the string, and it pulls up our weight.
There's a guy screaming in the background.
So we pulled the string and said stop. Okay. And our calculations, just in total, so our gear ratio of the mechanism was a 12.67. I missaid it in the video. Our total efficiency was a 13.4 because our AMA was the 58.82, and our ideal mechanical advantage was actually a 439.5 if we could get the gears to work correctly and greased up to where they would work without too much friction. We could lift something extremely heavy with just about no effort, comparatively. And the individual mechanical advantages, our first wheel here is a mechanical advantage of 2.83. Our second, so our final, the smallest, right here to pull the block and tackle string, was a 1.75. Our block and tackle had a 7 because it has the 7 supporting strings. And then we had our gear ratio total of 12.67, and to get our that's okay. And to get our complete, we just multiplied them all together to get our 439.5. And do we have any questions?
You have a brake system on there, why doesn't the weight go back down?
There's so much friction in our gear ratio, or in our gear chain, that it doesn't, we didn't put one in, but it doesn't move on its own because it's increasing by so much. This, no matter how hard you push on this one here, it won't move the rest of them. There's just too much lock in it. It'll stop itself unless you move the initial gear. So I mean, if you hooked it up to a motor, you wouldn't have to use any power to keep it there. I mean, unless you had something exceeding its weight limit. So you wouldn't have to use any extra energy to do it. It's just the energy you put into it to move. And just once again, I'm Chandler, this is Morgan, and Ahmed, and we're the Shamble Squad. If you want to move something straight up, call us.
I got one more question for you.
Okay.
So you said you didn't use a screw in the machine.
Yeah.
So how in the world is that staying together?
Oh. We didn't use a screw to move our pulley.
Okay, so but the screw was used,
Yes.
and the screws, you know, they have incredibly low efficiency because the whole point of the screw is a fastener, right? I mean, usually you're not, you know, trying to, move it or
Yeah.
you're trying to actually fasten it together. So you have and so you did use a lot of screws. Everybody used a lot of screws in the
Yeah.
thing. It's just for the part of the machine, it just wasn't in the actual mechanics of the stuff.
Yeah.
So.
And really half of our weight was in the, if we could have just slimmed it down a little bit, that we had limited stuff to work with.